All right, let's see. So according to what I've written over here, 151. The master set 4-5 applications is due officially Thursday, and we're gonna have class next week, and then the test is a week from this coming Thursday. So test in 9 days. Any questions? Okay. We left off. With the talk about energy and work. So let's do a quick review. Work is force times displacement. And the dot product deals with how much of the force is in the direction of displacement. So if I've got a box here that is going to move a certain direction, a certain distance, then if I apply a force in that direction, I will have positive work, because in this case all the force is in the direction of the displacement. So in this case the work would just be the force times the distance traveled in this specific case. Again, the box is going to be moving some displacement in that direction, but the force I'm applying is at an angle, some angle theta. Leave it slightly ajar. Then it's only the part of the force in the direction of motion that matters here. So the work is going to be the force times the cosine of theta times the displacement. The same is true here. It's still F cosine theta times the displacement, but theta in this case is 0, and cosine of 0 is 1. If the force is down and the object's moving to the right, what's the work done by the force this time? Is this force helping the movement? Is it hurting the movement? How so? I saw 2 people nod yes on that.
Because it's putting force down on the box. So there, is it frictionless?
All right, so indirectly it does harm. If there is friction, indirectly there is harm to it, because it applies a greater force downwards, which increases the normal force, which causes a resistance. But when we're talking about work, excuse me, when we're talking about work, it's a matter of whether it directly impacts it or not. It's the friction that is harming the movement, not directly this force. So in this case, the force is not harming it. This force is not doing any work. From the math equation of it, the angle between displacement and the force, so if my force is down and my displacement is to the right, what is the angle between them? Come on, anybody.
90.
Thank you. Units?
90 degrees.
There we go. And the cosine of 90 degrees is if a juror pull out your calculator. Indeed. And again, confirming that idea that no work is done. This would be positive. These are both positives. Now, if it is harming the work, so this object's going in this direction to the right, but the force is pushing against it. So think truck heading towards the baby carriage, and Superman jumps in the way to try to stop the truck from running into the carriage. So he's pushing against it, and he's being pushed backwards. So this force is now harming the movement, which is a good thing here. So harming is probably not the right word. It's detracting from the movement. That come up with your own verb. So this is doing negative work. In this particular case, the force is opposite my displacement. And so what is the angle between them if they're in opposite directions?
180 degrees.
There we go. And the cosine of 180 degrees is -1. If you don't get -1, then I suspect you're in radians instead of degrees. And that's where the negative comes in. So you can either think through it and go, oh, I know this is doing negative work, or just plug straight into the math and the negative will come out of the math. So the work is negative f of the distance. All right. So that's part of the recap. We have this idea of kinetic energy, so give you a moment to check your notes if you need to, because I'm about to ask for you to verbally, in unison, give me an answer. You probably should know what it is at this point. All right, so what is the formula for kinetic energy? That was less dynamic than before the break. But I do appreciate the two voices I heard.
Because we haven't done so long.
I know, this was, we're dusting off cobwebs at the moment. Let's try that again with feeling. What's the formula for kinetic energy?
1/2 mv squared.
At least that was more unison. I can't say much for the feeling involved, but we'll go with it for right now. Don't worry, you'll have other chances. So kinetic energy is the energy associated with speed. Potential energy, the energy associated with position. And what's the formula for potential energy? Doesn't have to be in unison. I'll take anyone with the correct response to that. Bless you.
MGH.
I was wondering if somebody would give me that one. That is actually not the correct response. That is the correct response to a different question, I should say. You might need to make a note of this. So, Amy, you were about to say?
Oh no, I thought I had it, but because someone
He said MGH. MGH is the most common answer to that question. Recognize that's a very specific type of potential energy. The correct response to what's the formula for potential energy is which one? That's the correct response. Now, just so that Amy and Ian have the correct answer, what's the formula for gravitational potential energy when the acceleration due to gravity is relatively constant? There we go. That's the time. So I'll just write down the various. These combined give us what is known as mechanical energy. And there is a third type of energy that I put in just mainly as a side note at this point, and that is rest energy. Which I get into more detail at the end of the second semester course. It's just mainly here for completeness. So just an extension of U there, U sub G, MGH, plus a constant. And this assumes little g is relatively constant. Probably inappropriate for me to have constant and constant. These are not. Little g is approximately, I'm just going to write out the word constant. This constant right here is just some number. It has nothing to do with the value of little g. And if g is not, so g is not approximately constant, then the formula is negative big G mass 1 mass 2 over R. So the first one, if you're dealing with things that are near the surface of a planet or a moon, the first one is the one you'll be using. If you're dealing with things that are really not dealing with outer space, such as Earth-Sun relationship or black holes, which we'll derive at some point, then this is the one that you would use. And a couple more things in our romp through what we did a week and a half ago, or a little bit more than a week and a half ago. There are two types of forces: conservative and non-conservative. So that's a V there. Conservative forces produce conservative work. Non-conservative forces produce non-conservative work, however the way that works. And this gets, now we have all the little bits and pieces. We have the three work energy relationships. We have the total work is equal to the change in kinetic energy. We have the non-conservative work is equal to the change in total energy, or E. And then there's the conservative work, which is the negative change in potential energy. Or you could just go to the base definition of work there, and the total work is also just equal to the total force times displacement. Non-conservative work is equal to the non-conservative force, total non-conservative force times displacement, and the conservative work is the conservative force times displacement. And that actually gets more and more slanted as I go. There we go. And I think that basically captures what we did 12 days ago. Presumably this brings back happy memories. Any questions at this point? I assume you're about to take a picture, Amy.
I can't really see a word, so it's kind of small.
Oh.
Or the one for total. Yes.
That's F subtotal. So the total force times displacement is equal to the work total, which is equal to the change in kinetic energy. Is that? Okay. Any other questions right now? All right, so let's actually apply this. We're going to start out with a simple example, and then we'll get into the ski problem relatively quickly. And in the process, smear the board. Rock. Follow. the initial speed at 0 meters per second. And I want to know, let's see, let's start out with a height of maybe 10 meters and 3 meters. I want to know how fast is the rock going when it is now 3 meters above the ground. The distances are different, but if you need a visual, that's basically what I'm talking about. Is I have an object, I drop it, how fast is it going at some point? Now this is a type problem that we should have been able to do from stuff we did in chapter 2. However, we now have a different way of doing the exact same problem. So first off, force diagram. Generally a good place to start. What are all the forces acting on the rock as it is falling?
Weight.
Yes. Is that a conservative force or a non-conservative force?
I kind of want to say conservative, but I'm not sure how to explain.
Okay, so you said conservative?
Mm-hmm.
All right, anyone have something a little bit more than Amy just feels that is right?
Unless I wrote it in my notes wrong, it says that it's a conservative.
Okay, so we have notes and
It just feels right.
it just feels right?
There's a formula for it too, right?
There is a formula. I didn't go into the formula. I just basically gave you a list. So, Amy, your gut feeling is absolutely spot on, and your notes are correct. Another hint is that we have a potential energy formula to go with this. That's conservative. For every conservative force, there's a potential energy formula. So mgh is the one associated with weight. All right. So it is a conservative force. Therefore, energy is conserved. I'm going to go through some preliminary steps that at some point I'm just going to skip past, but at least just to show how the work-energy relationships connect to this. So I'm going to start with the non-conservative work is equal to the change in energy. I have only a conservative force involved here. Therefore, what is the non-conservative work? So 0 is equal to my final energy minus my initial energy, because change in energy is always final minus initial. I'm going to add initial energy to both sides, and so my initial energy is equal to my final energy. So I went through a couple of steps here just to say energy is conserved. And again, conserved from a physics point of view means my initial quantity is equal to my final quantity. It's not about preserving resources. All right, I have two types of energy. So again, going through the steps. At some point as you get more comfortable, you can skip some of these steps, but for right now, I suggest not. So my initial energy is my initial kinetic plus my initial potential. Equals final kinetic plus final potential. I am assuming that this rock, as it falls, is not going to suddenly burst into flames. We're not going to have any energy matter conversion going on. So now it's formula time. What's the formula for kinetic energy?
1/2 mv squared.
Well, I do appreciate the 2.5 voices I heard. Initial squared plus, and then 1/2 mv final squared. What's the formula for potential energy? There we go. The one associated with weight.
That was the MGH, right?
That's the one, yes. So it's mgh initial, and over here mgh final. When you're comfortable enough, you can jump straight to this equation, but as we're going, learning the process. Now we can simplify it a couple of different ways here. Notice that we do have mass in every single term. And so we could just divide everything by mass, and mass goes away. So dividing this by mass, divide that by mass, and I'm left with 1/2 V initial squared plus G H initial equals 1/2 V final squared plus G H final. And now let's simplify one more time. We have 4 terms here. Again, terms in math speak is that what you add to something else. What can we get rid of? What's equal to 0?
Half by half.
Sorry?
The half on both sides.
Oh, you want to multiply by 2? You get rid of it? Okay. So if we multiply both sides by 2, times 2, we get VI squared plus 2GHI equals VF squared plus 2GHF. Nothing wrong with that, just so long as you multiply everything by 2, don't just get rid of the halves. But back to my question of, is any of this equal to 0?
I'm sure the answer is yes.
That is correct. What is equal to 0?
Oh, yeah, who's that?
Initial velocity.
Yes, initial velocity is 0, but more specifically, more important for us, initial speed. We're dealing with scalars here. So this is 0, because right here, amongst the cloud of previous marks. Now, anything else equal to 0?
Would it be final speed as well, since initial is equal to final?
Initial energy equals final energy. We can't comment on the speed. Well, from experience, I know the speed will not be 0. The rock never hits the ground. If you brought the ground into it, suddenly we have another force involved, which would actually be a non-conservative force, and so our energy would not be conserved in that case. All right. Just to let you know, it is possible that we have another value that's equal to 0. It depends on how you want to solve the problem. Traditionally, you do set it up to minimize the amount of math you have to do. So what I'm going to do here is, first we'll solve it given the silence. Let's solve it as if nothing else is 0. And then we'll solve it where we have an extra 0 in there. So we're now left with 2 times g, let's assume it takes place on Earth, times, what's my initial height?
10 meters.
Is equal to my VF squared, VF is what I'm trying to find, plus 2 times 9.8 times, what's my final height?
3 meters. -7 meters, maybe?
Negative, not the way we have things defined, it would not be -7.
Okay.
However, one of the ways I will solve it, we will have a -7 there.
Okay.
All right, so this is 196. It's equal to VF squared plus 58.8. So VF squared is equal to 0.2 there. 137.2. I subtracted what that over.
Yep.
All right, and so VF would be 12 point something.
11.71.
Was it?
11.71.
Yeah. I thought I had a mistake. 11.71. Now let's finish it off.
Meters per second.
Oh, yeah.
Yes. Meters per second. All right. We have an answer. We've used conservation of energy. If we had used the cake formulas, because acceleration is constant as it's falling, let's see, we have displacement is 7 meters, acceleration is 9.8 meters per second squared, initial velocity is 0 meters per second, and so we want VF squared equals VI squared plus 2A delta X. And so we'd end up with VF being the square root of 2 times 9.8 times 7. And I just have a strong feeling that somewhere around 11.7, maybe 7.1 if I wanted to. We should get the same answer. Acceleration is constant, so we could use decay formulas. Or energy is conserved, so we can use conservation of energy. We've got some choice. Now, if I made the ground, let's say I dropped it down 6 meters, is that going to change my answer? Okay, I got one person saying no, and is that a yes, it will?
It's a yes.
All right, so either of you, offer your thinking.
I guess it'd be changing the distance it's falling, right?
It's still going to fall, oh, because I said 3 meters from the ground?
Yeah.
I'm assuming it's still going to fall that 7 meters.
That's why I said no, because it's still following the same, you're still looking for the, I'm assuming you're still looking for the same, distance.
Yes, that was what my thinking was. I guess I didn't state that explicitly. So if it's still falling only 7 meters, despite where the ground is, would you agree that you get the same answer? Yeah. Okay. Sorry about the miscommunication. This would still hold true. That doesn't change. Over here, though, what changes? I know the answer is still going to be the same, but what would change in terms of the way we set it up? If I drop the ground 6 meters down more, what would the initial height be?
16. The 10 would change to 16.
And the final height?
Better be 9.
And that number would change, and that number would change, but the difference is still going to be, this is where it comes back again. So where we choose, when we're choosing our initial height, it really is somewhat irrelevant. And this gets into two things. One, the formula for potential energy here is technically mgh plus some constant. There's nothing special about this 10 meters here. What's special is the fact that it's going to fall 7 meters. So we can make h is equal to 0 here, in which case this is h is equal to 7. We can set height is equal to 0 wherever we want. And so if we do that, that becomes 0. If we set height is equal to 0 at the bottom of the problem, this becomes 7. And then that should jump us straight to here. Or, instead of setting height is equal to 0 here, I can set height is equal to 0 here. So if I made this height, or that height is equal to 0, then my final height is negative 7 meters. In which case, this becomes 0. And so we end up with 0 is equal to VF squared. Just trying to throw it on the ground. VF squared plus 2G, and then this would be negative 7. Now notice that it did not define the positive or negative direction here. And this is one thing different from vectors. From vectors, I can say, well, up's positive, so therefore down is negative, or down's positive, up is negative, and that's not a problem. But here, because of the way that MGH was defined when we created the potential energy formula, going down is a smaller number. So if this is 0, this is going to be negative. If that's 0, this will be positive. Right, questions to here? I'm about to give a problem that looks far more complicated, but it's not. It just looks potentially more intimidating because acceleration will not be constant. Made it a bit too high for